Hello, everyone. Thank you guys so much for coming out to our workshop, Less Quantum, More Computing. We're super excited to see all of you, and we hope that you guys enjoy our workshop. So to begin, let's go ahead and introduce ourselves.
So hi, everyone. I'm Ashley. I'm a second-year computer science and engineering student at CLA. And outside of computer science, I'm interested in dance and video games. My pronouns are she, her, and I'm really happy to be hosting this workshop for you guys today.
Yeah, and hello, everyone. My name is Vivian. My pronouns are she, her, and I'm also a second-year computer science major at UCLA. During my free time, I like to dance, and I'm also super excited to be hosting this workshop for you guys. We also have our lovely volunteers. If you guys would like to unmute and introduce yourselves, we can go ahead and go based off of this order. So Kenny, why don't you go ahead and start?
Hi guys, I'm Kenny. I'm a third-year applied math major and I'm super excited to help out for this workshop.
Hello everyone, my name is Eugene. My pronouns are he, him, and I'm a third-year CS major, and I'm excited to help out today.
All right, and I don't think Shrishti is here right now, so we can go ahead and go to Erica.
Hi, I'm Erica. I'm a third-year computer science major and environment minor.
Hello, I'm Raff. I'm second year linguistics and computer science major and excited to volunteer for this workshop.
All right, yeah, thank you guys. Those were our lovely volunteers. If you guys ever have any questions, feel free to DM any of them. They can go ahead and tell us your question, or also feel free to unmute. But yeah.
Yeah, and before we get to the workshop, we know that exploretech.la is hosting a raffle system, and the way that you can increase your chances of winning in the raffle is by getting points through workshops and panels. And so before we talk about the content, we wanted to give you a sense of like how you can earn points. So the first way is through general participation. If you ask any questions, or if you're getting a little adventurous answering any questions, you can earn some general participation points. Second way you can earn points is by participating in the Kahoot that we'll be hosting after we cover all of the content. And finally, if you're top 3 inside of our Kahoot, then you get the 1 extra last point.
All right, yeah. Also, we do have a review document that I will be dropping in this chat. This has a bunch of terms that we will be going over later in this workshop. So feel free to try to open it now. If you can't, feel free to also just message in the chat and we'll go ahead and fix that for you. But yeah, that is a handy dandy review sheet for your viewing pleasure. But okay, let's get back to the workshop now. Okay, so all right, now we have a lovely meme. And as you can see, the classical computer is pretty smart, but it's still pretty average. The quantum computer is a little bit brighter and able to do some more things. And finally, we have you after this workshop, and you're going to be the biggest brain. Okay, jokes aside, you guys are probably wondering, what will this workshop even cover? And that's a great question. So this workshop's learning objectives are to expose you guys to some quantum computing terms and concepts that form the basis of quantum computing, and to also hopefully inspire in all of you a drive to continue learning more about quantum computing after this workshop. All right, so now that we've talked a little bit about the learning objectives, let's go ahead and actually take a step back and get a little historical. So I don't know about you guys, but when I think of quantum computing, I think of like some futuristic stuff like Ant-Man. But the idea of quantum computing actually originated as early as the early 1980s. This guy called Paul Benioff, who is widely considered a pioneer in quantum computing, demonstrated the theoretical possibility of quantum computers by describing the first quantum mechanical model of a computer. Okay, and a little more recently, in October 2019, Google AI and NASA teamed up to use quantum computing to compute in seconds what would have taken even the most sophisticated supercomputer, which is just a really fast classical computer, thousands of years to finish. All right, so let's go ahead and go back to the future, but more forward. So really, the next thing we're going to be talking about is the future potential for quantum computing. All right, So one future application of quantum computing is leveling up medicine. Currently, scientists and pharma companies are experimenting with different ways to speed up finding medicine. The company Atomwise has previously used a supercomputer to find medicine quickly. Using a supercomputer, they were able to find 2 different medicine candidates within the day. Quantum computers can take this one step further by allowing us to simulate how drugs would affect different molecules. Now, you might be wondering if quantum computing can help us find medicine more quickly, then why didn't we do this at the beginning of the pandemic? And that's a very relevant question. The simple answer to that is our technology just isn't quite there yet. Researchers have theorized that it could be anywhere between 5 to 10 years before we can actually use quantum computers to level up medicine.
Yeah, and just to build up on that, quantum computers generally, the structure, they have to be in very rigid conditions in order for them to work properly. So in order to have like medicine be, in order to find medicine really, really quickly, we have to make sure that the conditions that a quantum computer in are really, really fitting to what it needs in order to work. And then that's another factor of why our technology isn't quite there yet. And before we get to anything quantum physics related, we wanted to show you guys this quote by renowned physicist Richard Feynman to give you a little sense of how to think about quantum versus classical computing. The key takeaway from this diagram is that the quantum computer can perfectly mimic nature, which is the collection of many, many things happening all at once. The classical computer, on the other hand, while it is able to copy some aspects of nature, it really can't live up to the full potential of what nature has to offer. And so in this diagram, you can see that quantum computer is perfectly mimicking nature, but classical computer, while it has the red mask and the black eyes, it's a little lacking and it can't really meet what nature is. All right, so now that you have that little intro, the first thing you might think when you hear quantum computing is, what exactly does quantum mean? Well, quantum comes from the Latin root quantus, which means how much, how many, or how big. And this relates to the definition of quantum, which means a small amount or the minimum amount of any physical entity. And this entity that is described inside of the definition of quantum usually relates to either energy or matter. And how does quantum have anything to do with anything science? Well, alongside of the word quantum, quantum physics is also a branch of physics that deals with very, very small particles on the size of the atom. And one such particle that you might be familiar with is the electron. So now that we've kind of discussed what quantum means, we want to start talking about the different concepts of quantum physics. And the first thing that we're going to talk about is quantum state. So you can think of quantum state as the collection of properties in a quantum system. And what properties can mean is, for example, for an electron, some properties of an electron are spin, momentum, position, and etc. So these properties of a quantum system usually exist in a superposition. And if that doesn't make sense, let's take this analogy of a quantum system as a piano. A piano has a property called note, and each note is a different state in which you have keys as the state. Whichever key or keys that you press at some moment in time would represent the quantum state of a piano. So just to reiterate, if you have the piano as the quantum state and you have a property of notes or keys, then each key represents one state of that property. Hopefully that makes sense, but if it doesn't make sense, our next definition may give a little bit more insight as to what exactly a quantum state is. So we mentioned that quantum states usually occur as a superposition of properties, but what exactly is a superposition? The Wikipedia definition is the ability to simultaneously be in multiple states at the same time. But to simplify this definition further, we can think back to our piano analogy. If each key is one state of the property of notes, then pressing down on multiple keys to play a chord would mean that the piano is simultaneously in multiple states at once. Another example can be seen with a regular light switch and a sliding light switch. If you can see on the left side of this slide, the regular light switch can represent a classical system, and it only has two states, on and off. The sliding light switch, which represents the quantum system, will then have the two states of on and off, as well as every combination of on and off in between it. If we take the top of the switch as completely on and the bottom of the switch as completely off, then the area between the on and the off portions of the switch is considered the area where any superposition of both on and off exists. The middle area is all of the, so the middle area can be seen as a fraction of fully on and a fraction of fully off at the same time. And that's what it means to have some property be in a superposition of states. It's simultaneously in multiple states at the same time. Again, we know that these definitions are really dense and they may be a little bit mind-boggling. And if you didn't understand that from those analogies, we also have another analogy later just to tie it together. But for now, we're going to move on to the last definition on this screen. So the last thing about quantum state is that it actually varies with space-time. And space-time just means where and when a particle is. All right, so we know that that was a lot of content. So if anybody has any questions at all, please do ask. This is going to be a very rough overview of all of the concepts. So definitely it may be hard to understand, but we want to help you understand. So please ask questions. Does anybody have any questions? You can like unmute, put it in the chat. Oh, okay. So Rufta Kabir says, when was quantum first discovered? Okay, so actually the timeline of quantum goes back to the 1930s. So quantum theoretical existence kind of started with the EPR theory that stands for Einstein, Podolsky, Rose, I believe. And in that era, people were mostly like testing the hypothesis of quantum, but they weren't really sure whether it existed or not. And around the 1970s, I think they started to solidify different types of algorithms related to quantum. And after that, in the 1980s, as Vivian said before, people started to theorize the fact like, oh, we can apply quantum physics to computers. And then now we kind of like developed over those times, and we've gotten to a point in 2019 where we're actually like executing and implementing quantum physics in computing, and we're seeing really cool results.
I have a question.
Yeah.
So how does quantum physics, I guess, being at multiple places at the same time or in multiple states at the same time, have to do with the speed of how fast a quantum computer can compute? Like, how do they go hand in hand, I guess?
Yeah, that's a super good question. And actually, it's something that we may be touching a little bit upon later. I might save your question for later for when we talk about like how quantum physics actually applies to quantum computing. But thank you for asking that question. We will get to that later.
Zara also asked a question in the chat. Zara asked, isn't Schrodinger's cat also a common analogy used to describe superposition?
Yeah, absolutely correct.
Yeah.
So Schrodinger's cat, if you guys are familiar with that analogy, is when you have a box and you have Schrodinger's cat is inside. But before you look into the box, you don't know whether Schrodinger's cat is alive or dead. And you guys can look a little bit into this theory outside of this workshop if you want. But the reason why we didn't use it is because it is a very commonly used analogy. And we wanted to see whether we could explain it in a different way.
Yeah. Does anyone else have any questions? Feel free to drop them in the chat or message one of our volunteers if you want to stay anonymous, or also go ahead and unmute yourself. Oh, okay. So Rufida, if I'm saying your name wrong, feel free to correct me. But Rufida asks, what are the cons of quantum other than that it's expensive? This is also something else that we will be touching upon in a bit later. But just so like you can get a feeling for it, another con would probably be that it's just huge. Like it's really big. Quantum computers can be really big, and it's really hard to like make them portable, which is definitely a con.
Yeah, and I did touch upon this a little bit earlier, but quantum computers require certain conditions in order to be fault tolerant, as they term it. They need to be in very cold conditions. Any type of heat will end up like altering the workings of the chips and the qubits. And so what happens then is like, that means anytime like anything that is not ideal for execution enters the environment, then the quantum computer loses its quantum state and is unable to perform its quantum abilities. Mm-hmm. So Zara asks, is quantum coding different than normal coding? So this one is a little bit interesting. I think in terms of the logic of coding, it's pretty much like the same, but like the ability, like the potential of what you can achieve with quantum coding is like a lot bigger than normal coding, just because of the existence of qubits, which we will touch upon later as well.
Yeah, quantum computing also leverages quantum physics. And in order for quantum computers to be faster than normal computers, they have to be able to leverage quantum physics. So there are like certain conditions where you can't use quantum physics, and in those conditions, quantum computers aren't that much faster than like normal computers. Okay, Johnny Go asked, how exactly can quantum computers simulate types of medicines to be used by pharmaceutical companies? This is a very good question. We don't have the exact specifics on this for you, but we can give you like kind of a rough idea of how it works. So the way like quantum computers can simulate types of medicines is that you can use something called like quantum circuits to like replicate what molecules in like the human body kind of like interact with like different drugs. So in by allowing like drugs to like interact with like molecules, by allowing the simulation, you're basically able to kind of like guess or predict what will happen in like an actual human being. And the reason quantum computers are better at this than like supercomputers is because they're faster at it. So they're able to like do the simulation at a much quicker pace. And this is because they're able to leverage like quantum physics.
Yeah, and to piggyback on that idea, if you think back to the definition of superposition, it means to be able to take on multiple states at once, right? And inside of nature, simulations means that you need to be able to have like multiple things happening at once. Whereas a regular computer mostly does sequential work, a quantum computer is able to, you know, take on those multiple states and allow you to see like the different possibilities of which medicines you can create.
Yeah, so if anyone else has any questions. Okay, it looks like nobody else has any questions at the moment. But if you do come up with anything, feel free to drop in the chat and we'll respond to you. But for the sake of time, we're just gonna keep going for now. But yeah, if you do have any questions, feel free to drop in the chat.
Yeah, they're really good questions, guys. All right, so we talked about superpositions and quantum states. So now what we're going to look at is something called measurement. Okay, but are we looking at it or is measurement looking at something? So that's a joke based off of the definition of measurement. And measurement is basically when a quantum system is looked at or observed. So somebody brought up the theory of Schrodinger's cat, and measurement is a very key concept in it. before you look at a quantum system, it can be in any possible state or superposition of states. So before you look at it, it's going to be, you don't really know what is inside. However, what measurement does is when you look at a state, then you have to force it to take on a state, because for you visibly, you wouldn't be able to comprehend the idea of something being in multiple states at once. And so if that doesn't make sense, we can kind of bring in this analogy and say we have like a bag of magical color changing marbles. And so this bag of marbles is going to be the quantum system. And this quantum system has the property of color. And each marble inside of the bag will either be the state red, blue, green, or yellow. And before looking inside of the bag, you really don't know what is inside of the bag. You don't know which state it is in, because it's in a superposition of all of the different states of colors. However, say you want to look inside of the bag. Now the bag is forced to pick a state and stick with it. And on the screen, we chose green, but it could have chose blue, yellow, or red. And this is the process of collapsing a superposition of states to a singular state. Hopefully that makes sense. It's like when you measure a system, or when you look at or observe it, you force the superposition to assume a singular state. And that's particularly what collapsing a quantum superposition means in the context of things. But hopefully, if that didn't make sense, we also have another meme to tie it all down. So in this diagram, the male is an observer who is unable to see the superposition of quantum state that exists before looking at the quantum state. He can only see the female in the red dress, which is the observed quantum state. And it defines how measurement and superposition works. Aha, how funny. This is also a moment in the workshop where you can ask any questions about measurement if you do have any. If you want to like take a moment to like absorb the slides, we also have the document that you can look at. But if nobody has any questions, we'll also move on to the next topic. Okay. So for now, I think nobody has any questions. So we're gonna move on. All right. So this is gonna be like the last big quantum physics concept that we're gonna cover in this workshop. And you guys have already learned quite a bit already. So this is a huge accomplishment. Now that we've covered measurement, we can start talking about the entanglement of quantum states. So Albert Einstein termed this concept spooky action at a distance, because entangled particles knew about each other even when they were incredibly far away. The basic definition of entangled states is that the state of an entangled particle depends on the state of its entangled partner. And what exactly does that mean? Take marbles again as properties, and different colors as the different quantum states. Suppose in this case that we only have two states, green and blue, and we place these two entangled particles in two separate boxes and ship them off to very far places around the world. One of the boxes gets opened in, say, California, and the observer measures and finds that his marble is the state green. He automatically assumes that the quantum marble in the other box shipped to Russia is the color blue. But why? Well, two marbles that are entangled particles have states that depend on each other. If we know that one of the particles is the color blue, and there are only two states, then the other marble must be the color green. So this is the idea of entanglement. A quantum particle must have one state if its entangled partner has another. So I'm gonna let that sit. Hopefully that does make sense. If you guys don't really get it, well, we can try to elaborate on any questions that you have, which is the purpose of this slide. I was really confused when I first learned about this stuff too. So yeah, if anybody has any questions.
Wait, so how does quantum computing actually allow it to be faster than normal computing?
Yeah, so we are going to talk about this, but so quantum computers utilize something called qubits. And since qubits are able to take on, okay, well, Vivian is going to talk about this more. I think another person also asked a similar question. So after Vivian talks about like qubits, we'll elaborate on any confusions that you might have. But thank you for that question.
Yeah, mainly it's because we need to define what qubits are before we can answer this question. But it's a really good question, so thank you guys for like asking them. I think yeah, 2 of you guys asked these questions, and thank you guys for asking them. We will define qubits, and then afterwards we'll take questions for that.
Does anybody have any questions related to quantum state, superposition, measurement, or entanglement? Okay, I think that's a no, but if you do in the future, feel free to ask it. And we're gonna quickly move on, and so that we can get to the qubit question.
Okay, so just one more slide before we actually get to like the bulk of the qubit stuff. But now that we've talked a lot about like quantum physics, you might be wondering, but how does this even apply to like a quantum computer? Like, cool, we learned all these terms. Now, like, let's get to the computing part. And this is that. So your question might be, what is a quantum computer? And well, a quantum computer is a computer that leverages quantum physics, such as superposition and entanglement, to perform calculations and store information. More specifically, quantum computers store information inside of these things called qubits, which we'll talk about a bit more in the next slide. Okay, so before we can actually talk about qubits, we first need to talk about this concept of bits. So bits are the basic informational unit of computers, and they're used to store 2 states, typically a 0 and 1. If you remember our light switch analogy from when we were talking about superposition, then 0 would correspond to being off and 1 would correspond to being on. Okay, so now that we've talked a bit about bits, we can now talk about qubits. So as mentioned before, qubits are the basic informational unit of quantum computing. Qubits can be 0, 1, or a superposition of these numbers. If you recall from our light switch analogy, this would be similar to if you had a dimmer and you set the light to be in between on and off. If that example isn't super clear, then we have another analogy for you. So qubits can also be thought of as a spinning coin. So when you have a spinning coin, do you think that it's heads, tails, or both? I'll give you guys a couple of seconds to think about this, and when you have an answer, go ahead and drop it in the chat. So we'll go ahead and wait a couple of seconds. Just if people want to drop it in the chat. If you guys do drop it in the chat, you guys will get participation points for this as well. Yeah. Okay, so now that we've waited a bit, Tony said it depends on the current position at a specific time. Yeah, and that's very close. It would depend on a position and a specific time, but in this case, since the position is spinning, and the time is like when it's spinning, the answer would be more of it's actually both heads and tails at the same time. And this is because of the idea of superposition, because it's can simultaneously be in 2 states at once. So similar to that coin example, qubits can be in a superposition of both 0 and 1. And this is going to go back to that question where you guys asked, how are quantum computers faster than normal computers? And the reason why is because of this property of superposition in qubits. So because qubits are able to be in a superposition of both 0 and 1, they're able to make calculations for like 0 and 1 and like the possible states in between at a faster rate, so that they don't have to like do all of the calculations at once. If Ashley wants to hop in and give maybe a clearer explanation, feel free to.
Yeah, so as Vivian said, the key idea here is superposition. So usually for a normal computer, you can only go either 0 or 1. But with a quantum computer, what you now have the possibility of doing is exploring all the different routes at the same time. So you have 0, you have like 1/4 0, you have like 1/2 0, and on and on and on. And you do all of these calculations at the same exact time. And what this ends up giving us is quantum computers, which can calculate things at an exponentially large, faster rate. So it depends on how many qubits are inside of the computer. But if you take a computer that has only 8 bits, this is just an example. Normal computers don't really have 8 bits, but if you had a computer that had 8 bits and you had a quantum computer that had 8 qubits, the normal computer would be at a rate of like 8 computations, but then the quantum computer would end up having a rate of 2 to the 8, like the speed of how many computations it can run at once. And if that doesn't make sense, it's okay, because it can be a little bit weird, but basically depending on how many qubits you have, your rate at how much computations you can do at a single point in time exponentially increases by a factor of like 2. Hopefully that makes sense.
And if you guys have any questions about that, feel free to ask, because I know a lot of people were asking about this before.
Yeah.
So Zara asked, if quantum states in superposition are represented in sphere, is it kind of like how values are shown in a unit circle?
Yeah, so that's a good question. It is slightly like that, except the reason why I think quantum states are represented as a sphere is because if you think of the sphere's z-axis as like what a person would normally see, and every surface point of the sphere as like the superposition of all of the different states, depending on whether the vex, or I don't want to go too much into like math, but depending on whether your state is above the 0 axis or below the 0 axis, when you end up measuring that quantum state, it'll collapse to either like above or below the axis. I don't know if that makes sense. It's really hard to explain without like a visual. It does kind of, it is represented as a sphere though. And the unit circle is also a pretty good comparison, but since the unit circle is 2-dimensional, it's not as accurate of a comparison.
Yeah, if you have any other questions, feel free to drop them in the chat.
So Rufita also said that 0 and 1 is making me think of binary code, and that's completely correct, because 0 and 1, we use these 2 examples because computers typically use 0 and 1 in order to write, their information in binary. And if anybody doesn't know what binary is, it's just a different way of representing information that computers use.
All right, yeah, so it looks like we don't have any more questions coming in at the moment. If you do think of questions, feel free to drop them in the chat, but for the sake of time, we might move on just a bit more. Oh, this is actually just a meme to like help solidify the difference between like bits in a normal computer and like qubits in a quantum computer. So as you can see here in this meme, a normal computer, which would use like bits that can only take a 0 or 1 and nothing in between, would be either yes or no. But then a quantum computer, which stores their information in qubits, which can have a superposition of 0 and 1, is actually, well, yes, but actually no. And this is due to that property of superposition. All right, so now let's go ahead and compare quantum computers versus like a classical computer. So now that we've like covered some of the concepts behind a quantum computer and what a quantum computer is, you're probably wondering what the difference between a quantum computer and classical computer are. So although classical computers are fast, quantum computers are much faster when they're able to leverage quantum mechanics. And that's like an important part. If quantum computers aren't able to leverage like quantum physics, then they won't be faster than classical computers by like a lot. they'll probably be like on the same playing field. So it's very important that quantum computers are able to leverage quantum physics. And quantum computers are really good for like math intensive operations, such as optimizations and simulations, which we briefly like mentioned with the medicine. While classical computers are good for your like more day-to-day activities, such as sending out emails or like joining a Zoom, like you guys are all doing. Quantum computers are also able to store more states in their qubits than classical computers. So for example, qubits can be 0, 1, or a superposition of 0 and 1, like we talked about before, while classical bits can only be 0 or 1. Okay, now you may be wondering, if quantum computers are faster than classical computers, why aren't they like everywhere? Why aren't they just used everywhere? And the answer to that is, for one thing, quantum computers are much more expensive. They're much larger in size. They require much more energy to run than your typical classical computer. And as Ashley mentioned before, quantum computers require very like specific conditions to be able to operate within. And if those conditions are not met, then the quantum computers risk like damage, being damaged. So it's very hard to like move them around and make them portable, which is why they're not like widely used everywhere. Okay. So although quantum computers are fast, it's very unlikely that classical computers will get replaced anytime soon, mainly because of all those reasons we just listed.
Yeah. And so now we're kind of nearing the end of the information related to quantum. And so right before we get to the Kahoot, we wanted to just do a quick review of all the concepts that we covered so that you're prepared to win that. Okay, so the first thing we kind of talked about was quantum state and superposition. So quantum state is going to be the properties of a quantum system that usually exist in a superposition. And what was a superposition? Well, a superposition was the ability to simultaneously be in multiple states at the same time. Next, we talked about measurement. And what happens with measurement? Well, if a quantum state usually exists in a superposition, then when you start looking at it or when you observe it, then it forces that system to collapse the superposition of states to only a singular state. And finally, we talked about entanglement, which is when the state of one quantum particle relies heavily on the state of another particle. And you aren't able to define the quantum state of one entangled particle without defining the state of another quantum particle. Hopefully that was a good, very short review.
Okay, yeah. So we're also going to review the concept of bits and qubits. So as you may remember, bits are the basic informational unit of computers. They're used to store two states, which are typically 0 or 1. Qubits, on the other hand, are a special type of bit that quantum computers use to store their information. So qubits can represent all possible combinations of 0 and 1, as well as 0 and 1 themselves. So basically, qubits can have a superposition of 0 and 1, and that's that property is what allows them to be faster than classical computers.
All right. And so now that we've covered all the concepts, we're going to, tie it all up with a Kahoot.
Yay!
All right, let's go.
That handy dandy review sheet. If you guys want to open that up while playing the Kahoot, that's totally fine. Go ahead and use it. But yeah.
Yeah, we also want to note that if you end up creating like an inappropriate nickname for yourself, we will have the ability to kick you, as well as if you want to earn points for, participating in the Kahoot and potentially winning, you have to use your real name. Otherwise, we won't be able to like record those points for you.
Yeah. Also, while we're waiting for people to get on, if you guys have any questions, feel free to ask. Oh, also, just a quick note, you guys will also be getting access to like the slides and the Kahoot and like the review sheet, I think after this event. Within our slides, we do have like the answers for the Kahoot. So if you guys like want to look back on it sometime in the future, those answers are available for you guys on the slides. Okay. I think we might.
How many volunteers versus students do we have here? I think like 18 people total means.
We should have 12 people because there's 6 Explore Tech staff or volunteers.
Okay. think we have, oh, yeah, we have 11 here. So
If anyone's having any problems getting onto the queue, okay. I think that is everyone.
yeah, okay. So I'm gonna start it now. Okay, so that was really, really fast. So quantum computers will eventually replace regular computers. The answer is false, but we will elaborate more on this in the next question. Ooh, looks like we have some fast fingers in here.
All right, yeah. And here's our second question.
All right. So we have most people getting the answers. And to elaborate on why quantum computers won't eventually replace regular computers, is just because they're kind of like too much. They're more than what we really need for everyday life, right? Most people aren't going to be using quantum computers because all they really need is like just do everyday normal tasks. And so quantum computers wouldn't be able to like make up for the cost benefit of just an affordable, regular portable computer. Another thing about why quantum computers are not widely used is, as you see on the slide or on the page, is cost, and it takes too much power for everyday use, as well as the points that we mentioned on the slide that we will share with you guys later. Ooh, okay. We got some shifting in the ranks. You guys are getting pretty competitive. Let's see Leela in the first slot.
All right, yeah, let's go, guys. It's okay if you guys aren't in the top couple. Like, you guys can still make a comeback. Let's go, guys.
Woo! Awesome. Okay, so we have true as the answer to the question. This is pretty much a definition question. So if all of these definitions seem a little shaky to you, definitely check out the review sheet. And yeah.
Yeah, also, if you remember back from our slides, a couple analogies that we used to like explain superposition included the piano pressing multiple keys at once, the dimmer with like the dimmer being in between 0 and 1, and as well as the dime or coin spinning, the ability to be in both heads and tails at the same time.
Oh my God, Leela's on fire. Okay, but Tony's catching up. We got people coming up.
All right, yeah,
let's keep it up. Let's go.
All right, guys.
All right. So this may have been a tricky question just because when we define quantum state, we talked a lot about like being in a superposition of states. However, the definition of a quantum state is actually the properties of a quantum system. So yeah, it is, yeah, another definition question. Definitely was a little bit of a trick question. See if you can like, get y'all to answer wrong, but most of you guys did get it right. Ah, shucks. Just kidding. I'm not that kind of teacher. Okay. Oh, we have a change in the rankings. Wow, this is really, really interesting.
We love to see you guys climb in the ranks. Let's go, guys. You guys are doing amazing.
And even if you're not in the top, you're learning a lot, which is really cool.
Yeah, you guys are amazing just for being present.
We love you. Oh my God. Okay, so quantum state varies with space-time, and this is true. This is another point that we mentioned on our quantum state slide. So yeah.
Yeah, this is more of a definition kind of thing. But yeah, quantum state does vary with space-time, which just means that quantum state depends on where you are and when you are.
Wow. Okay. We're seeing some shake. Matthew on a streak of 5. Okay, you got this.
Let's go fire. Also, don't worry if you guys aren't in the top couple. You guys still get the participation points, which counts, which actually does count more than getting top 3. So no worries about it.
Ooh, tricky. So measurement. Somebody answered kilometers. That is actually kind of true. Not gonna lie, kilometer is a way to measure something. However, that's not the definition that we were alluding to in our slides. So the definition of measurement is actually observing a quantum state and collapsing it to a singular state.
Yeah, and somebody else also chose the ability to simultaneously be in multiple states at once, and that is the definition of superposition.
Cool. Love seeing this. We're on second to last question.
Yes, Ashley, I don't know about you, but I think qubits are pretty cute.
Oh yeah, they're hella cute. Okay, so nobody picked cute bits, kind of sad, but they would have gotten it wrong, so maybe it's good that they didn't pick cute bits. So indeed, qubits are quantum computers' method of storing information. Oh my goodness, Adam P. Yo, you're on fire. This is our last question.
All right, guys, what are bits?
Cool. Okay, so we have 2 of these are actually the correct answer, and it seems like almost everyone got it right. So yes, bits are a computer's method of storing information, and they're typically represented by ones and zeros. Let's see. Who's the winner?
Ooh, let's go. All right, let's go third place. Oh, Joanne.
Joe. Rosita, eh?
Who we got?
Oh, who's that?
Okay, let's go.
Adam P. Yo. Okay, so we have our runners up, Tony and Matthew as well. You guys are star students. Okay, but everyone is a star student, but y'all are kind of impressive.
All right, yeah. So that does. Wait, Ashley, before you exit out, just go ahead and stay on that for a bit so our volunteers can jot down the names. But yeah, that does end up concluding our workshop. Thank you guys so much for coming out. Oh, Ashley, did you?
Wait. I think we have extra resources slides that we want to go over before we conclude. So after our volunteers have finished writing down these names, we'll go over those quickly, and then y'all are free to go.
Yeah. All right. Okay, I think the volunteers are good, so we can go ahead about our resources.
Okay, so as we said before, all of the questions are also going to be on the slides that we're going to be distributing later, so you can take a look at that. We also have some slides that we didn't go over for the sake of time, and this is related to like actually coding with a quantum computer. If you want to, go into this in your own time, feel free to do so. We have all the tutorials linked over here, as well as a Jupyter notebook through Google Colab, also linked on here that you can just follow through and run. So all the instructions are here. But some other things that we wanted to talk about is that, like, over the course of this presentation, like, we talked about a couple of concepts of quantum, but it's not necessarily all the very cool things that quantum can do. And some other cool things that, quantum does include, well, these things you can search up, but the double slit experiment is often referred to as one of the first things that people are into when they get into quantum, as well as quantum tunneling, Shor's algorithm, and cryptography. All of these things are things that people think are really, really cool about quantum. So if you have some time, you can go check those out on Google or something. And for extra resources, the thing about quantum is that it's not all conceptual, and there's a lot of math and physics involved. So we don't want to like pretend that quantum is a super easy subject and that you can like get it in 1 hour. So it's really hard. But if you're looking to get into quantum computing for real, we recommend that you study linear algebra and physics really, really closely, as well as if you know about IBM, they have an open source software called QuizKit. That's basically an open source quantum computer that you can play around with. And it's also the activity that we linked above. So if you are interested in like exploring quantum a little bit further after this workshop, that's something you can look to. And finally, we have gotten to the end of our workshop. And so now is the time, if you have any questions about anything, you can stay and ask us. But if not, feel free to leave. We really appreciate it. For coming to our workshop. It was really, really fun. Vivian, do you have any last comments?
Oh, yes. Also, I do believe IBM does make like YouTube videos and tutorials for the QuizKit stuff. So if you just search up on YouTube like IBM QuizKit tutorials or something, things should like pop up. We'll probably also link it in the drives like somewhere around the extra resources. But yeah, thank you guys so much for coming out. If you guys do have any if you guys have any questions, feel free to ask us. Yeah, thank you guys so much. We hope you guys enjoyed our workshop.